So I have been talking about neutral atom quantum computing, and there is a review article which you can use as a reference to look up various things. So the important feature of this realization is generation of 2-qubit interactions through Rydberg blockade. Okay, because otherwise the atoms are neutral, they don't have the static electromagnetic interactions. You have to somehow convert it into a large dipole, which is what Rydberg atom does, and then you use dipole-dipole interaction to construct various 2-qubit transformations. So the last thing which I mentioned in the previous class was generation of a Toffoli gate, which I didn't completely specify. So I checked the algebra. Actually, it is not Toffoli gate, but it's related to it. It's a double control Z gate. And the point is that all three qubits need to be in the same Rydberg blockade region. Which means if you excite one of them, you cannot excite the other two at the same time. And under that condition, the transformation which I wrote down does the correct job, and it had a 5-pulse sequence. So it was a pi on C1, pi on C2, 2 pi on the target, pi the reverse order, and pi on C1. And this produces minus of the CCZ gate. That can be verified without too much trouble, and it's something which is useful to note because these 3-qubit gates you can certainly break down into 2-qubit gates, but that breakup results into some around a dozen transformations, and if you can implement it directly, it will save much effort. And also this Toffoli gate is a easy implementation in reversible quantum logic for both addition and multiplication. So it occurs in many algorithms, and having a simple realization of it is an advantage. So this is one version of implementing 2-qubit and 3-qubit operations. There is another version which was designed by the group of Mikhail Lukin at Harvard University, and it does something similar but using less number of pulses. So it's more complicated in terms of its implementation, but saves some time. And what he came up with is it's a 2-pulse implementation of a gate which is similar. So, well, there is a conversion in terms of some notation, but that is okay. So, it is 1 e raised to I phi e raised to I phi. So, the scheme which he developed implements this particular logic gate, and it's not exactly the control Z because this angle phi appears as a extra stuff, but the e raised to phi I phi can be absorbed in redefinition of the qubit state, which you can indicate as 1. So, this is 0 0, it does not have it, but this has 0 1 1 0. They can be redefined, and then all these phases 1 1 can be absorbed, and then it looks like a control Z operation. And the way this is implemented using only 2 pulses is a clever choice. First of all, this is a diagonal gate, which means whatever state you start in, you have to complete a cycle and come back where you were. So, all states complete what are known as Rabi cycles. So, you end up where you started, and in the process you pick up some phase, and that is the cleverness of the algorithm. So, the cycle will require going to a excited state and coming back. So, both these 0 1 and 1 0 go through the excited states, which will be in this notation. Which one I couple to the excited version, it does not matter. I will just write it one part. So, if one completes a cycle, it has to go through a virtual state and come back, and that virtual state I use as a Rydberg state in this particular notation. So, it will require some laser pulse or some particular frequency, but this combination with 1 1 goes through a coupling which is a little bit different. Because both of them cannot be simultaneously excited. So, either the first one gets coupled to R, or the second one gets coupled to R, and in a particular scenario, what you have is a superposition of these possibilities normalize correctly, and this is the kind of virtual state it will cycle through and come back to its starting point. And because of this, it's possible to insert phases inside this process, because the routes which these things can be described by on a block sphere are slightly different. It's a one going to R, but in some different manner in different situation. So what they have, first of all, there is all pulses which are used they are slightly off the resonance frequency. They are detuned to make it to address the correct location, etc. as usual. But something more is done is that between the two pulses, the orientation of the driving field, the laser transition, which induces the rotation, is that you apply one pulse around one axis, the other one is perform a rotation, and then again apply the pulse accordingly. Remember, when you apply a rotation about the z axis, the locations in the x and y plane change. So that is where the difference comes in. So the result is that the Rabi cycles, whatever it is, are not great circles, but closed loops on the block sphere. And that makes a whole difference. You are coming back to it. You started at this, but it's not going around the great circle, it's going around some other side loop. And when you do that, you have to now do the evolution of the single qubit with some rotated axis. So it completes a cycle, but then the phase which is picked up is not pi. The phase is the solid angle enclosed by that particular loop. Okay. That is a part of topology which you need to check by doing a little bit of algebra. So if I draw say a block sphere, the complete great circle rotation will go through the opposite states and come back, but another loop can go around some other orbit and come back to the starting point. And then the question is, what is the corresponding phase which for this particular kind of transformation? It's given by the solid angle subtended by that loop, and the origin. In this extreme case, it was just pi, because the solid angle is just a hemisphere in that particular case, but in this particular case, the angle can be different. And what the trick which is used is adjust this relative orientation of the two pulses so that this solid angle picks up the desired phase of pi. Okay. The phi is just a 1 to r coupling. It will also be some rotation, but that is not too complicated. It is common everywhere and it will be picked up all the time. The more complicated job is to produce this phase pi, and for that you have to use certain ratios of what is this rotation angle and what is the corresponding frequency of rotation, because that decides the duration of the pulse, and the total angle is, well, the product of the two, whatever the strength is there and the duration of the pulse, and that relation has been worked out and it is there in the article by Lukin. They found the required numbers and they use it, and once that is done, this is the gate which is obtained, which is little bit shorter in time because it uses 2 pulses instead of 3, and well, every little bit helps you reduce the length of the logic operation. You can do more logic operation in the time available before the whole system decoheres. So that is what is done, and they have had good success with performing various kind of transformations. Yeah.
It is I of 2 pi minus pi or 2 I pi minus
The pi is separate. Yeah, or the I is there everywhere. Okay, fine. Okay, so just some numbers which are quoted in this paper. So they are important for practical point of view, that the fidelity of single qubit rotations is, they can achieve more than 99%, and fidelity of 2 qubit rotations, and also measurement is greater than 95%. So this is the current status of this particular realization.
Sir,
Yeah.
clarify that using this gate, the angle subtended by the closed loop is the phase.
Is the phase, yeah.
For the analysis. Now, how is phase of pi achieved using this?
Well, you have to do the calculation, it's a particular ratio which appears, which they determine. All these things are involved. There is a certain amount of detuning. Okay, so the detuning shifts the frequencies in a little bit from the resonance, and that decides again the time you require to complete a cycle. This driving field is rotated. That means the circle which is completed by the first pulse is not the same as the circle completed by the second pulse. So one of them will give this, the other one will give something there, and you have to find the difference between the two, and they adjust them, and that adjustment produces this e raised to I pi. They give a ratio of the two frequencies, and this what you call the angle of rotation between the two pulses to specify what is given by pi. It requires some calculation on this solid angles on the sphere, but it's a fixed number. If you want to produce pi, it is some number which you have to use. Okay, so that much about this computation, but there is another interesting scenario which appears with the same setting, and that is analog implementation, which means we directly simulate a model and see its evolution in time. This hardware basically just becomes a copy of the model that you want to simulate, and you are not doing any digital algorithm or anything directly inside it. And here this whole situation is two-dimensional and three-dimensional models with specific lattice geometry can be realized. And there are lots of models of this type which you find in whatever condensed matter physics. You define certain set of qubits or spins on a lattice, and you want to see how they evolve in time. Okay, of course, the results are all in a so-called non-perturbative region where you would like to see how things happen. Perturbation theory, if it works, then you don't need to do any simulations at all. So there are different versions of it. So the simplest one is a so-called Ising version, where ground state and the Rydberg state they form the two basis states. Remember, this is completely different than the digital one, where the basis states were the two hyperfine states of the atom, and the Rydberg state was only virtual one. Here, this is literally interpreted as a part of the Ising model. You needed two states. This is what you identify with that, and then there are various terms which you can write down in the Hamiltonian. So there is a, I'll just write it schematically. Some frequency which directly couples to a single spin, and that is like in any other model where you can well, I have to put the components as well. Okay. So if I put sigma x here, it will take you from the transition from one state to the another one, and this is a so-called this Rabi oscillation interaction term. It can take you from the whatever the state 0 to state 1 and back and forth. There is a corresponding frequency, and depending on the duration for which you apply the Hamiltonian, you can do a complete oscillation or a part of it or whatever it is. So this is one of the terms. Then there is a second term which also appears in the description, which is the number operator acting on the state j, and again some strength. So I have to put some okay, this is okay. Let me put some coefficient alpha. So where does this thing come? And this is just a diagonal term for every spin, and its energy is shifted because there is detuning. Some you are not at the resonance, but a little bit off it, and whatever amount shifts, this alpha j is detuning, and that term kind of appears. And then the third term, which is the repulsion, which can be made to look like this after the shifting the what you call 0 and what you call 1. So in the state 0, this one is absent, or even if one of them is 0, the term is absent. But when both of them become 1, there is a repulsion, which is the Rydberg blockade strength. Okay. So you can take a particular configuration and it will generate this kind of model. And then the question comes is this model useful somewhere? Okay. And that comes to the question is what all kind of realization of this Ising version you have used in statistical physics. Can this be fitted into somewhere? The answer is yes. And this model can be mapped to some well-known scenarios. One of them is called Hubbard model, which is some interaction between various spins but with a hardcore repulsion. And this Rydberg term produces that hardcore repulsion kind of naturally. Then there are problems involving frustrated spin systems, some of them, which can be mapped into this kind of scenario. Again, the frustration arises precisely because of this repulsion term. You can't have everything satisfied at the same time. And going back to a more general kind of things which computer scientists deal with, they are called combinatoric optimization problems. So these are the problems on typically described on graphs. So the lattice is directly mapped into the graph, and certain kind of edges will become this interaction. And the purpose of this combinatoric optimization problem is to minimize or maximize some function. That function could be the Hamiltonian in a quantum scenario, and you can't find the optimal solution easily because there are constraints, and that is where the combinatoric part comes in. So the Hamiltonian has certain properties that no, every term cannot be optimized simultaneously. There are constraints, and certain combinatoric problems can be mapped onto this kind of situation as well. And so the strategy is to create this kind of structure by putting these atoms on a lattice with Rydberg interaction and just allow it to equilibrate. It will do its own dynamics, but it will finally reach a steady state, and then measure properties of that steady state. And they will tell you various properties which you are looking for in these physics models. So this is the analog version, which actually has also been used quite a lot by the same group of Mikhail Lukin, and they have done various geometries. It could be hexagonal lattice. I think even the Kagome lattice has been tried. They have tried something even in 3-dimension structures, some lattice, but not a perfect geometry, because you have to always put in some frustration inside the system somewhere or the other, and then try to figure out its properties. And these properties, all kind of so these are correlations. But since you are looking at the time evolution, you can even observe non-equilibrium properties, how the things are going, which includes things like dissipation. Then correlation means production of large entangled states. Then even defects. There's something you take out from the lattice, and there is a gap left, and how does it change the evolution, all kind of features, they have been studied in some manner. And these kind of things may be qualitative. You don't have to really work it out to high accuracy, what all these things are, but they tell you about the behavior of the physical system directly, how things are working. And many times getting an idea about what is going on is useful even when you don't have the high precision available. So that is a kind of structure, and some people have gone even beyond. So what is known as yet another model, not this Hamiltonian, but something which is known as a XY model in quantum statistical physics, and that uses actually two Rydberg states, but one of them, the radial excitation number n is the same, but one of them is an S wave and the other wave is a P wave. And if you do that, you can model this XY dynamics also, of course, because the states are excited, lifetime is much smaller, but people have tried mapping that as well. It's a kind of variety to see that, yes, you can do all kind of structure. The limitations are one of them is that there are imperfect arrays in loading itself. In the last lecture, I had mentioned that when you take these optical tweezers and put atoms inside it, the fraction which actually goes into specifically marked locations is about half of them. The other half are empty. That is something which nobody has optimized much better than that. And so you create an array, but it's not a what you call a uniform array in physical space. And so when you are studying a model like this, there are lots of gaps. And so it will not exactly model a lattice which is fully filled. And in that situations, the couplings which you are putting inside here are not going to remain the same everywhere. There are holes, there are what I call various kind of defects, etc. And you have to figure out what to do with it. So models with full symmetrical structure actually don't come out very well unless the error is small. And large arrays, there are problems. You can't do a good job. You try to do whatever you can in a limited sense. And other thing is the lifetime. So how long do these systems live before it decoheres? So there is something called a quality factor which in this scenario is about 100, and the way this is defined is a number of uh, oscillations till so this is a term which is taken from classical wave dynamics. The waves are not perfect, they decay in time, and the question is how many oscillations it will be able to perform before the whole system decays, and that object is called the quality factor. So in the analog mode, the quality factor which is achieved for these models is about 100. So if you can study some properties within these limitations and find some useful understanding, you can achieve it, but that are the kind of limitations which you have in this particular situation. And what is the state of the art in terms of hardware? That is a recent paper which came out, which I would like to point out. It is from this Amazon Center at Caltech, and they have not done any computation, but they were able to make a large optical tweezers. So this just came out last month or something like that. There was a paper, so they were able to load about 6,000 atoms in a trap which had about 12,000 locations. As I said, the filling fraction is about half. But these numbers are becoming large. People can create this optical tweezers with what you call a large pattern, and this is a two-dimensional kind of structure. Linear chain just would become too long to be able to be realized, but two-dimension it's quite okay. And the points are some of the accuracies which so this is two-dimensional room temperature, and in high vacuum. As I have explained, once you have high vacuum, you can have the thing that room temperature doesn't matter very much, but then they could measure all these properties. So coherence time is about 10 seconds. Then the numbers they quote, these are not operations, it's just preparing these traps and holding these atoms in place. So there is something called a survival probability. That means once you put that atom in the trap, does it remain there or fall out? They could do it a excellent job on that. And there is something called imaging. Can you see them? and that has even one more line added to it. So these things are very much what you call in the technological control, and the reference is uh, archive 2403122021. So yeah, now once I've made this trap and filled it with various kind of atoms, they will try something that will come out in next few months, what they are able to use this kind of large system for. Much more likely in the analog mode rather than in the computational mode, but it's making things possible to reasonably good fidelity, and that is a technical achievement.
So, what are those number operators represent?
Number operator just means the state is occupied or not.
So, like, is it a phonemic mode in this data set?
It will, well, the oscillator language is a dagger A.
But like in terms of this Rydberg blockade, like what kind of
Here the Rydberg blockade is a fermion. So fermion has only two occupation numbers, either it is 0 or 1. That's all.
and also like you had mentioned, since these Rydberg states are very large, hence there are certain selection rules also, right, that determine the transition. So
Yeah.
dynamics, because we are considering this spins like Euler systems.
Yeah, because you are dealing with excited states, you have to worry about all the lifetimes and whether the things will remain available for that particular time where you can do whatever evolution operations, whatever you want to perform. But yeah, the excited states are always unstable. So there will be those kind of terms which I have not written down at all.
And why is there the read unit type?
Hmm?
What's the purpose of the read unit type?
Just add some extra coupling if you want. In experiments, it is always there because you never work directly at the resonance. It is always little bit detuned because otherwise the system is not stable. You put too much energy inside it, will all break up. That's all. The number n, yeah, it's occupation number of that particular state. Ground state you call it 0, the other state you call 1, whatever it is. It can be translated in the sense that it's a, well, there are various ways of writing this kind of thing, but here it is directly if you want to map it the Rydberg state, then you call that the Rydberg state is n equal to 1, the ground state is n equal to 0. Hmm? Yeah, so see, there is a some notation which you have to, well, translate from one language to another. For example, in the Hubbard model, what you have is a structure where there are operators which cause transitions, which will, like a kinetic energy, takes from state I and to go state J. Okay, so there they are like AI dagger, AJ kind of terms. But then the the Hubbard model has also a term which is literally the number, the particle number, which means A dagger A at I multiplied by A dagger A at J. Okay. So that is the way the numbers appear over here. In this particular case, if you want to call Rydberg atom mapping with this Ising version, then Ising variables are labeled by 0 and 1. Okay, so 1 is the Rydberg state, 0 is the ground state, and then this term is non-zero only if both the atoms are in the Rydberg state. If you, yeah, there's a little bit of a mixture of the notation in going from one place to another, but you can sort it out. I mean, well, if you want to write it a little bit differently, don't write it as Ni and J, but write it as a sigma Z, some complicated version. So let me see now. Rydberg state is sigma Z equal to -1. This is excited state. The ground state is equal to +1, so it will look like 1 minus sigma Z I 1 minus sigma Z times J. If you want to write it in Rydberg rotation, this is what Ni will refer to. And it's a quantum model because some places there is a sigma Z, but there is some other place there is a sigma X as well. If everything was sigma Z, it will become a classical model. Hmm?
Why there is no repulsion when both the electrons are in ground state? I mean, math is fine.
Because the distance between the atom is kind of too large. The Rydberg atom was like micrometer size distance between the nucleus and the electron, which creates a large dipole moment, and this is a dipole-dipole interaction, which enters the description. That's why the interaction is not in the ground state. The nucleus and the electron are very close by, and the distance is too large, so it does not create a large dipole interaction.
So like for the Ising model, we can think of it as a simulation of some dipole-dipole interaction, right? But in a Hubbard model, as you mentioned, it's more like a Hawking term.
Yeah.
The state is being like operator, like there's some transfer of some quantum to the other state. So how is that interpretation always via the
You can do a mapping, that is what it is, but directly what this analog structure, it will realize a Hamiltonian like this. The question comes is whether the model you want to be studying, does it map onto this or not. If it can be mapped, then you can study. If it cannot be mapped, then you can put it aside. So it's not that all kind of models will be studied. Model with some specific properties will be related to the structure, and then you can understand something. So this now brings me to the last topic which I want to discuss in this particular course, and it is called measurement based quantum computing. It's a departure from all the circuit technology which we have used so far, and it also has some practical advantages, and it's worth understanding what the principles of these things are. It's sometimes also referred to as one-way quantum computing. It decides that it is monotonic evolution in time, irreversible, and you start somewhere and at the end you will have the result. And the fact that it is measurement based, it's because of the dynamics which has three parts. So one is prepare a highly entangled quantum state, then perform a sequence of single qubit projective measurements, which is definitely probabilistic. And the third is correct or combine the probabilistic outcome means you have a whole distribution. But then you combine all these various outcomes in a very clever fashion by certain kind of correction, so that the result is deterministic. And these are words, but the point is it can be done. And all the tricks are how this procedure is implemented, and the fact is that it's a universal algorithm, which means that whatever you can do in any of the circuit model kind of stuff can also be done here. And many times it is given a acronym, which is the combination of these three steps, which is entanglement, measurement, and this correction. So of course there must be some tricks involved in here. Okay, it cannot be as simple as that. But now I have to specify. You want to create an entangled quantum state, but it must be possible to create it very efficiently. Otherwise, the algorithm will break down. You want to perform a measurement. Measurements are probabilistic, and so they are arranged in a clever manner. And most important part of the clever manner is that a result, or rather the setting of a particular measurement, depends on the results of all the previous measurement. It's not fixed a priori. Okay, it depends on what all you got in the earlier measurement, and the new direction will be decided by them. So these are the tricks. This entangled state, and of course all these words will become explicit only when I work out the examples, show that this can be indeed done. Um, Measurement direction refers to the fact that I am just going to perform a single qubit projective measurement, but projection along what direction that I am allowed to choose. Okay. And these corrections they are not arbitrary, they will depend on all the measurement results. And the job is to now set up a scenario which demonstrate that yes, you can do all these tricks one by one and get where you and implementation is done very easily on photonic platforms. The advantage of this photonic platform is that if you leave the photons alone, they don't interact with each other at all, and all you are doing is successive measurements which you can do with photons by adjusting the direction of the polarizers, and between them the photons are left to survive for themselves. They are not fixed qubits. They are traveling, so they will go through some waveguides or whatever structure you need to make, but they will not get disturbed while they are propagating, and only polarizations. So there are things like that, polarizers, beam splitters, and waveguides. These are the usual ingredients in quantum optics.
How are the entangled states attained in photography?
Yeah, I will come to that, how you describe it. So right now, let not me worry about this hardware part. We'll write down the Hamiltonian and the gates in the usual qubit language, and finally come back to the question about how you will implement the various gates. For example, polarizers is quite frequently used for measurements, that you have an axis and you want to find the component along that, you use a polarizer. So this is a measurement. What beam splitter does in optics is, again, you have to remember half of it is going one way and half of it is going to another way, and that is this Hadamard operator. One of them will involve a reflection which will give a minus sign. But the beam splitter is a unitary operator, and what it does is actually implement this Hadamard gauge. Waveguides are for propagation. Okay. So the initial state is something which is called the cluster state. And it is described by a graph, which means some vertices and some edges. So every vertex you create what is known as a plus state, which is obtained simply by taking a zero state and applying the Hadamard operator. And that every link or edge is applied. So this is whatever graph is, every time there is a link, apply a CZ operator. And that's it. So this is highly efficient in the sense that I can do this thing simultaneously on all the vertices in one clock cycle, completely parallel. This also, how many edges are there? All these CZs commute another clock cycle, and in 2 clock cycles this state is prepared. That's all you need. So parallel implementation in 2 clock steps. And this is it, there is nothing more. Some graph, of course, all the tricks about the algorithm depend on what is the graph that you are going to select. Okay? But once you have the graph, this is the state you are going to prepare. Nothing more than that, and that is a kind of straightforward. How you prepare this CZ, well, you can write down the same kind of interaction as well. So whatever. So sigma z equal to both of them become equal to -1, then only this can be written. So it can be expressed as sigma z. This is a trivial stuff, but doesn't matter. That is possible, but there is another version which is useful in dealing with this photonic stuff. By 2 qubits which form either a singlet or a triplet, and singlet is an eigenstate, triplet is another eigenstate, but there is one of them here and the other 3 are here, and that 3 and 1 splitting you can map into this CZ 1, 1, 1 and -1, provided the energy of the singlet is not the energy, different from the energy of triplet. So you can take a 2 qubit system which has a singlet triplet splitting, and then you can label them as a CZ operation for certain evolution. So whatever the strength of the splitting is, you evolve for a certain time, it will produce a phase of pi. So these are meant just various ways, but these are the physical connections which turn out to be useful. It's not that every time you use the same interpretation. There are many possibilities. Okay. Yeah.
Which vertex acts as a control on the edge?
Doesn't matter, it's symmetric. So now this is essentially all you need for the first part. What is that you are going to prepare? What is it that you are going to measure? So you need certain directions in this block sphere, whatever you want to measure, but you can simplify it to certain choices of this Euler angle kind of rotation. So, measurement operator which is used is similar to what is used in NMR. It's specified by some direction in the xy plane and some angle theta. This is enough because I always have the z direction, and in NMR case, once I have the specification of z operation and any other operation in this xy plane, it is complete in the sense that I don't need to go arbitrarily to any point in the block sphere. This is enough to realize, and this is what is used, and you can write this quite simply as a 2 by 2 matrix. So, x and this is y. So, the structure is this. And the point is that this is sufficient for a universal setting, because remember whatever we used in NMR, it's quite similar. You have the operation along z and operation in the xy plane, single qubit operation. You have the Hadamard operator and you have the control z operator. And they form a complete set for performing any logic gate transformation, except that here these are not logic gates, these are measurement operators. So, you have to now connect this measurement to how it will convert into a logical operation. So, what is important is actually the eigenvalues of these operators, various things. So, eigenvalue is not important, rather they are very simple. The 2 by 2 matrix, trace is 0 and determinant is -1. So, one eigenvalue is +1 and other is -1. They are kind of trivial. The binary result will use all the time anyway. The question is, what are the eigenvectors? And then they can be very easily solved for, and I will write down in a single notation. So, there is a linear combination of 0 and 1 with a phase of e raised to I theta. It's very easy. If you take, for example, two component vector like 1 and e raised to I theta, that is what this correspond to. Take this and multiply, and you will see that you will get back the same thing. If you take a plus sign, then the first row, this multiply the phase cancels, you will get 1, and the second phase you will get back e raised to I theta, etc. so far. Okay. So, this is these are what the vectors are. And what is important, are the settings of these vectors, in the sense that you want theta to be variable, so I can make measurements along any of these directions in the equatorial plane. Okay. And yeah, to another restriction, this whatever I mentioned in the third step, actually these are correction operators, and there is again a restriction which is used that only x and z operations are used for correction. I won't use all kind of complicated things. These are again very specific choices, and that is sufficient. You don't need anything more. So now is the stage to demonstrate how it works, starting with very simple example, and that example is teleportation. Remember, teleportation was a situation where you had a state in one location, it disappears from that one location and appears in the other location. And it was done by, in the usual protocol, by using a Bell pair or untangled state to create and then send some messages across. So we are not using or not going to use any untangled pair, but effectively this control Z operation is going to take care of it. So this goes through a very simple graph which has only 2 points connected by this prescription of CZ, and by construction I'm going to put the state which has to be teleported on one location and another location is a vertex, regular vertex is a plus state. Okay. So now the job is to perform a measurement here, which will reduce it to some state, but we are going to discard it because it becomes a classical state, some eigenvector. And when you do that, the psi will appear here. Okay, that's a job. So this measurement doesn't mean that I will measure every single qubit, not necessary. I will measure some qubits, they will be turned into eigenvectors and classical, but the remaining qubits will still remain quantum, and they can describe the final state, whatever it is. So final state of unmeasured qubits, it provides the output. Okay, so now the measurement had all this theta, etc. Inside here. In this particular algorithm, I am just going to use theta equal to 0. So that is enough. That will give teleportation. That means I am measuring in the x basis. Y is not going to appear. So theta equal to 0, which is x basis. So now that's just to do the calculation. So initial state is psi plus, I'll have to expand, write it more generally. So let me write let a times 0 plus b times 1. Okay, that's fine. So what is the prescription here? The initial state is Cz, which is this link applied between psi and plus. And what did it produce? So you have to write in explicitly. It is 0 and plus. 0 is not going to get affected by the control Z. So it will be 0 plus. But when this one is 1, the component of plus, which is in the direction of 1, will change sign. So this will become B1, and that state where the one component is freeze goes from plus to minus. Remember, plus is 0 plus 1 and minus is 0 minus 1. Okay. So this is the initial state. Now you perform a x basis measurement on the first qubit. So, well, x basis is again plus and minus in some sense. All this is a 0 and 1 are the z basis, so you flip it around. So when you want to take x basis, you have to project this onto plus, and that will give the positive eigenvalue, project it into minus, it will give the negative eigenvalue, etc. So let's just do that. And I'm not interested in the outcome of the measurement in the sense of calculating the eigenvalue. I'm more interested in the outcome of the measurement, which gives me the state. So what will be the it produces the eigenstate of x basis, which will be sometime plus and sometime minus. What is the probability? I am not worried about, but suppose the eigenstate produces plus. Okay. Then how often that will occur? Well, you have to find out the projection of all those things in this direction. So there will be some 0, some part of it will go into plus, and then the other part will remain. A times plus is the second qubit. But there will be some plus component which will come from here as well. And that is the part which is again overlap of plus with 1 is same as overlap of plus with 0. So the coefficients are the same. 1 by root 2 I am not bothering to write down, they are all over the place, but that is taken care of the normalization. And when will I get minus? Well, then I will get the overlap of minus coming from 1 will produce a minus sign. So there are going to be two outcomes. Sometimes I will get this, sometimes I will get that. How often I get? Well, that depends on all the overlaps, etc., which I'm not bothered about. But this gives this is a result eigenvalue. What is it? This is plus 1 and this is one eigenstate and the other eigenstate. I call it plus 1 and minus 1. You can call it 0 and 1, it doesn't matter, whatever it is. Or this is minus 1 raised to 0, this is minus 1 raised to 1. Okay, we want a binary language, that is the trivial mapping. And now comes the correction step. This is the first qubit which has been measured, and I'm going to discard it. I want to convert this to get psi. Okay. So how do I do it? Well, one part is easy, that I apply h, which will take plus to 0 and minus to 1. That was the usual rotation. So I will get a 0 and 1, but there is a wrong sign here. How do I get rid of that particular sign? Well, I apply z to the power of this, z is the eigenvalue. So it's either this or so s in 0, 1 and minus 1 raised to s equal to t is in plus or minus whatever notation. So I take, there are two outputs, but by applying this operator, h is a constant operator, doesn't matter, but this operator depends on the result of the measurement. And its job is to flip this particular sign. So both the outputs by this action get merged into the same thing. And that is this particular point, that it combines multiple outputs to produce a deterministic result. That you have transported this state from this location to the other location by first preparing this and then just a simple measurement and a little bit of correction. And this algorithm, it now generalizes to a more useful setting. So what is called gate teleportation. So you have some gate on one qubit, you can transport it so it acts on the second qubit. And well, that and other kind of tricks which will demonstrate the universality of this scenario, I will cover in the next class.